Okay, picking up. Again, you got to remember everything we learned about indefinite integrals earlier. So things that you learned earlier. The integral of 1 over the quantity square root of 1 minus x squared dx was sine inverse of x plus c. The integral of 1 over 1 plus x squared dx was tan inverse x plus c. And then making those a little more general, instead of having those ones there, the integral of 1 over the square root of the quantity a squared minus u squared dx was sine inverse u over a plus c. And the integral of 1 over a squared plus u squared dx is 1 over a tan inverse u over a plus c. You really need to have these memorized. And so when we throw these guys in here along with 1 over x, these are the fractions that we're happy with. We know fractions of this form, they go to sine inverse. Fractions of this form go to tan inverse. And anything that I can make into the form 1 over x or 1 over u du, that goes into the natural log. That for now, those are the three fractions that we really don't mess around with, that we know the answers to these three fractions, or anything we can make look like these three fractions. And then I have that right down here. Also, 1 over u du is the natural log of u plus c. Those are the fractions that we don't mess with. All other fractions for now, you have to make go away. Now, when you get to Calculus 2, you're going to learn a lot of other techniques to try, but right now, these are the three fractions that we know how to deal with nicely. Okay, evaluate each of the following. And so I have to just really look at things and see if I can make it match a pattern that I already know. And I can pretty easily make it match this. That I can take that 3 out, and so that's 0 to 1, 1 over the square root of 2 squared minus x squared dx. And then I can just use this guy up here. Use that 1 over the square root of a squared minus u squared d. That should be a du right there. There's a typo. Two typos. Those should be u's. We'll try to fix those someday in the future. That's not a big deal. Is going to be sine inverse u over a plus c, in this case with a equal 2, and in this case u equal x. So I'm using that formula that I have up there, but in this case with a equal 2 and u equal x. And so this is going to be 3 times sine inverse x over 2 evaluated from 0 to 1. And now we do the evaluation. Plug in the upper limit, plug in the lower limit, and subtract. And again, plugging the 1 into the sine inverse and plugging the 0 into the sine inverse separately. That you plug in the upper limit totally by itself, you plug in the lower limit totally by itself. And now we're going to do that arithmetic, or trigonometry, not arithmetic. So remember, you're asking yourself here, what angle between negative pi over 2 in radians, negative pi over 2 to pi over 2 has a sine of 1/2. You absolutely need to know those basic unit circle angles and values. So you're asking yourself, what angle on the interval from negative pi over 2 to pi over 2 has a sine of 1/2, and that is pi over 6. And then you're doing the same thing on the end here. What angle from negative pi over 2 to pi over 2 has a sine of 0? And that is 0. And so my answer here is pi over 2. Now remember, your calculator can do these things, T83, 84. Now I've got an 83 here, so an older model, but it will do it. So you press math. You arrow down till you see FNINT, hit enter. The 84s actually give you a template that you fill in. The 83 is an older one, but if it's a template, just fill in the parts. Now the older ones here, you start with the integrands. So 3 divided by the square root of 4 minus x squared. For the older ones, you have to end that parenthesis for the square root. Newer ones, just be sure you exit that square root. Then it's comma x for the older ones. That represents the dx, the x. Then comma the lower limit, comma the upper limit. On the newer ones, the TI-84s, and I don't have an 84, the 83 was bought for me by the department long ago. Maybe I should come up with the money and buy myself an 84, but this works for me. Type it in there, hit enter. It's going to think about it for a while, and it's going to give me a decimal. It is working differently than we are working. It's not working by finding an antiderivative. It's actually doing a version of a Riemann sum. It really is. Some sort of bizarre version, but it's adding lots of things up. It's not working the way we are. But you can check your approximate value. So now if I ask the calculator what it thinks pi divided by 2 is, we hope those two numbers match, and they do, so we are right. So you are welcome to use your calculator to check these things. You are not welcome to use your calculator to find the answers definitively. I need to always see your work. But that one checks just fine. Okay, on to the next one. More of the same. Okay, so here we are going to use that the integral of 1 over a squared plus u squared du is 1 over a tan inverse u over a plus c. So let's just make it look like that first of all. So bringing that 3 out, that's going to be the integral from 0 to 1 of 1 over. Now I got a 3 here. To make it into the form a squared, I could call that the square root of 3 squared. So now I have that a squared plus x squared dx. And so this is with a equals square root of 3 and u equal x. And so that 3 can just stay out in front. And so this is going to be 1 over the square root of 3 tan inverse x over the square root of 3 evaluated from 0 to 1. And now we're going to do the evaluation. So that square root of 3 can come out with the 3, so I have 3 over square root of 3. And then tan inverse 1 over the square root of 3 minus tan inverse of 0 over the square root of 3, which give me 3 over square root of 3 tan inverse 1 over the square root of 3 minus tan inverse of 0. And we've got to figure those things out. So trying to figure out the tan inverse of 1 over the square root of 3. So my little thought process here is this, that we've got tangent of theta will equal 1 over the square root of 3, or sine theta over cosine theta equals 1 over the square root of 3. So the fundamental question I'm asking myself is, what angle between negative pi over 2 and pi over 2 has a tangent of 1 over square root of 3? I have to break it down into sine and cosine. And so then when I look at this, I match these guys up. And I ask myself, what angle on negative pi over 2, excuse me, should be open, to pi over 2, what angle on this has a cosine that involves square root of 3. Notice I didn't say equals square root of 3, I said involves square root of 3. And I break it down to sine and cosine because those are the numbers I know. Well, the answer there, that is pi over 6. Cosine of pi over 6 is square root of 3 over 2. And so I get to put a pi over 6 here. And then doing the same thing with the tangent inverse of 0. Now, some of you may really know your tangent values very, very well. And if you know your tangent values very, very well, you're not doing this. But tan inverse of 0 means tangent of theta equals 0, which means sine theta over cosine theta equals 0, And a fraction is only 0 when its numerator is 0. That's the only way a fraction is 0. A fraction is only 0 when its numerator is 0, period. That's the only way a fraction is 0. So I need sine of theta equals 0, which is going to tell me that theta has to equal 0. So minus 0, and so I get an answer of 3 pi over 6 square root of 3. And you could rationalize that if you want or not. I don't care if you rationalize it. If you do rationalize it, that's going to be square root of 3 pi over 6. You couldn't pay me to care about that last step. Either one of these are perfectly fine. And then you could check this on a calculator as well, just like we did the other one. But the point here is this inverse trig stuff is going to creep up, and so you do have to be able to work with those inverse trig values. Okay. Next problem. Definite integrals and u substitution. And if you look to the next page, we see, I'll put the next page beside each other. If you look to the next page, we've got the same problem twice. Because there are two ways you can handle definite integrals and u substitution. So I'm going to do it two ways, and then after I do it two ways, I'm going to always do it my favorite way. But you can pick whichever way you prefer and do it that way. But there are two ways to do it. So on the next video, because I'm not going to try to rush through it to get into my 15 minutes here, on the next video we're going to do these two problems. But let's note that it does have to be a u substitution, because I've got a composition. I've got tangent, and inside the tangent I've got pi over 4 natural log of x. I've got a composition and a quotient that I can't simplify away. And so our only choice that we have right now for things that we can't simplify are u substitutions. So this problem is going to be a u substitution. That if I have compositions and products or quotients that I can't simplify, my only choice right now is to try a u substitution. Now as you go through Calculus 2, you'll get a lot more choices. U substitution is not always what way it's going to be, but here, if it doesn't simplify, we got to hope it's going to be a u substitution. And that's what we'll see in the next video.